you ever stopped and thought about this? How is it possible that a machine weighing over 500,000 kilograms doesn't just lift off the ground, but calmly flies across oceans for hours? Today, we're breaking down how airplanes actually fly. And I promise, after this video, you'll never look at a takeoff the same way again. To understand the scale, think about the Airbus A380, the largest passenger aircraft ever built. Its maximum takeoff weight is around 575 metric tons. That's roughly the weight of a fully loaded freight train. And this thing doesn't just hop into the air. It climbs to 35,000 to 40,000 feet and cruises at around 560 miles per hour for 10, 12, sometimes 15 hours straight. By common sense, something that heavy should be glued to the ground. But physics says otherwise, and everything you see in modern aviation is the result of over a century of science, engineering, failed prototypes, and relentless experimentation. At first, humans learned how to rise into the sky using hot air balloons, but that wasn't true controlled flight. That was floating. In the 19th century, Sir George Cayley separated the concepts of lift and thrust and realized that wings needed a specific shape. Otto Lilienthal made hundreds of glider flights, studying how air behaves around a curved wing. Then came the breakthrough. In 1903, the Wright brothers proved something revolutionary. A heavier-than-air machine could achieve controlled, powered flight. Their airplane stayed airborne for just 12 seconds, but it changed the world forever. After that, progress accelerated. World War I pushed rapid advances in engines, aerodynamics, and aircraft structures. Metal airframes replaced wood. Designs became stronger and faster. In 1952, the de Havilland Comet became the first commercial jet airliner. In 1970, the Boeing 747 connected continents at scale. And decades later, the Airbus A380 proved that even a 500-ton aircraft could be efficient, quiet, and remarkably stable. But despite all the innovation, the core principle never changed. Flight is always about balance. So how does all that metal actually stay in the air? The answer lies in four fundamental forces. Every airplane in flight is governed by 1. Weight, gravity pulling it downward. 2. Lift, generated by the wings, acting upward. 3. Thrust, produced by the engines, pushing it forward. 4. Drag, air resistance, slowing it down. Think of it like a dynamic balance scale. When lift equals weight, the airplane maintains altitude. When thrust equals drag, it maintains constant speed. The moment there's an imbalance, acceleration happens. If the net force points upward, the aircraft climbs. If it points forward, it accelerates. There's no magic involved, just forces in balance. But that leads to the real question. Where does lift actually come from? You've probably heard the common explanation. Air traveling over the top of the wing has a longer path, so it must move faster, which creates lift. That explanation is incomplete. Lift exists because a wing changes how air moves around it. A wing has a specific airfoil shape, curved on top, flatter underneath. And during flight, the wing is angled slightly relative to the oncoming airflow. This is called the angle of attack. As air flows around the wing, the flow over the top accelerates. Pressure above the wing decreases. Pressure below remains higher. That pressure difference produces an upward force. But that's only part of the story. The wing doesn't just create lower pressure, it also deflects air downward. And according to Newton's third law, if the wing pushes air downward, the air pushes the wing upward with equal and opposite force. Bernoulli and Newton aren't competing explanations. They describe the same physical process from two perspectives. Lift is the result of pressure differences and the downward deflection of airflow. That's what keeps hundreds of tons suspended in the sky. One of the key factors that determines how much lift a wing produces is the angle of attack. This is the angle between the wing's chord line and the oncoming airflow. When a pilot pulls back on the control column during takeoff, the nose rises and the angle of attack increases. That changes the pressure distribution around the wing. Air over the top surface accelerates more, pressure drops further. Circulation around the wing increases, and the airflow is deflected downward more strongly. As a result, the lift coefficient, CL, increases, and that means lift increases. But there's a limit. Lift doesn't increase forever with angle of attack. It grows only up to a certain maximum value, known as CL max. Beyond that point, the airflow over the upper surface can no longer stay attached. It separates, pressure distribution collapses, and lift drops sharply. That's what we call a stall, and this is where speed becomes critical. Lift is described by the equation. You don't need to memorize the formula. One thing matters. Velocity is squared. That means if speed doubles, lift increases 4 times. If speed is cut in half, lift drops to 1/4. And we're talking about airspeed, speed relative to the surrounding air. The faster the airplane moves, the more air mass flows around the wing each second. The more air it can redirect downward, the more lift it produces. That's why an airplane can't just jump off the runway. Before takeoff, it must accelerate until lift equals weight. At that exact moment, the airplane lifts off, not because it became lighter than air, but because aerodynamic forces reached equilibrium. We already talked about pressure differences. Now let's look at the same process from another angle: momentum. A wing doesn't just create low pressure. It creates a pressure distribution that causes the airflow behind the wing to tilt downward. This is called downwash. Every second, an enormous mass of air flows around the wing. Aerodynamic forces change the direction of that flow, giving it a downward component of velocity. And according to Newton's third law, if the wing gives the air downward momentum, the air gives the wing equal upward momentum. Lift is essentially the rate of change of momentum of the air. The airplane isn't sitting in the sky, it's continuously interacting with the airflow, redirecting it. But what happens when the aircraft needs to fly slowly, like during takeoff or landing? That's where wing high-lift devices come into play. If you look out the window before takeoff, you'll see the wing changing shape. Flaps extend from the rear, slats extend from the front, creating a slot. Aerodynamically, this does 3 main things. 1. Slightly increases the effective wing area, S. 2. Significantly increases camber, the curvature of the airfoil. 3. Dramatically increases the lift coefficient, CL. The increase in CL is the most important factor. It allows the wing to generate much more lift at lower speeds. Slats serve another crucial purpose. The slot allows higher energy air from below to flow over the upper surface, helping the airflow remain attached at higher angles of attack. This delays stall. That's why aircraft can safely operate at much lower speeds during takeoff and landing. So why do commercial jets cruise at 35,000 to 40,000 feet? At those altitudes, the air is much thinner. Drag is lower. Fuel efficiency improves. Drag depends directly on air density. The denser the air, the more resistance the aircraft experiences. By climbing higher, the airplane reduces drag and burns less fuel per mile. There are additional benefits. Cold air improves engine efficiency. There are fewer weather systems and storm cells, less turbulence caused by terrain and surface heating. As fuel is burned, the airplane becomes lighter. That allows it to gradually climb even higher during the flight, a procedure known as a step climb. So how does takeoff actually happen? Takeoff isn't just full throttle and go. It's a carefully calculated sequence of speeds and actions. Before the aircraft even lines up on the runway, pilots calculate several key speeds. V1, the decision speed. After passing V1, the takeoff must continue, even if an engine fails, because stopping within the remaining runway may no longer be possible. VR, rotation speed. At this point, the pilot gently pulls back on the control column, increasing the angle of attack. The nose rises. Lift builds rapidly. Then comes V2, the minimum safe climb speed with one engine inoperative. This ensures the aircraft has enough performance and controllability to safely continue climbing. During the takeoff roll, part of the airplane's weight is still supported by the landing gear, but as speed increases, lift increases. At a certain moment, lift equals weight. The normal force from the runway drops to zero. The airplane doesn't jump, it simply no longer needs the ground. That's liftoff. After climbing out, the aircraft transitions to cruise altitude, typically around 35,000 to 40,000 feet. This is the most efficient phase of flight. In cruise, lift equals weight, thrust equals drag. There is no acceleration. This is a state of dynamic equilibrium. Now let's talk about descent and landing. Descent is not falling. Pilots reduce thrust and manage the aircraft's energy. Lift remains present, but becomes slightly less than weight, allowing the aircraft to descend in a controlled glide. Before landing, flaps are extended. The lift coefficient increases. The minimum safe airspeed decreases. This allows the airplane to fly safely at lower speeds. Just before touchdown, pilots perform the flare, gently raising the nose. This reduces the vertical speed and softens the landing. After touchdown, spoilers deploy, destroying remaining lift. Thrust reversers activate. Brakes are applied. Lift rapidly decreases, and the aircraft's full weight transfers onto the landing gear. Every time you watch a massive airliner lift off, it feels like it's defying gravity. But it's not breaking the laws of physics, it's using them. Lift, thrust, drag, angle of attack, everything exists in precise balance. To me, that's the real beauty of aviation. Not magic, but exact calculations and respect for the laws of nature.